Hey everyone, and welcome to the Energy Explorer Show. I am your host, Nicole Pearl Oyam, together with
Joyson A. Sibas.
Get Ready for an amazing journey of discovery.
Today we're uncovering the incredible power of energy. From the sun's warmth to the dazzling northern lights, we'll explore how energy travels, creating both everyday warmth and spectacular light shows.
We will discover how the sun's energy reaches the earth, warming our planet through conduction, convection, and radiation. And we will see how that same solar energy creates the aurora.
It's a journey from sunlight to starlight. Let's get started. Hey everyone, I am Teacher Joyce. Today, we're diving into a topic that's both fundamental and fascinating: the relationship between heat, temperature, and energy. These three terms are often used interchangeably, but they are actually quite distinct. Are you ready to explore? Okay, great, so let's get started. First, let's define our key terms. First is temperature. Temperature is a measure of the average kinetic energy of the particles within a substance. Think of it as the average speed of all those tiny atoms and molecules jiggling around. The faster they move, the higher the temperature. For example, a hot cup of coffee has a higher temperature than a cold glass of water because the molecules in the coffee are moving faster on the average. Now, heat. Heat is the transfer of thermal energy from one object to another. It's not something an object has, but rather something that flows between objects at different temperatures. Heat always flows from a hotter object to a colder object until they reach thermal equilibrium, or the same temperature. For example, when you touch a hot stove, the heat transfers from the stove to your hand, causing your hand to feel warm. And lastly, the energy. Energy is the capacity to do work or cause change. Thermal energy is a type of energy that's related to the temperature of an object. The hotter something is, the more thermal energy it possesses. But remember, heat is the transfer of the thermal energy. For example, a hot water in the kettle contains a significant amount of thermal energy, which can be used to boil the water and make tea. Okay, so let's proceed to the misconceptions and clarifications about the heat, energy, and the temperature. So now let's address some common misconceptions about heat and temperature. Heat and temperature are not the same thing. You can have a large object at a low temperature contain more thermal energy than a small object at a high temperature. Also, heat doesn't just involve temperature differences. It can also be transferred through radiation, conduction, and convection that we will be discussing later. So to recap, temperature measures average kinetic energy. And then heat is the transfer of thermal energy, and then the energy is the capacity to do work. Understanding these distinctions is crucial for comprehending many scientific concepts. Let me know in the comment section if you have any questions regarding with this topic. Now, let's proceed with the heat transfer. We all know that heat transfer has the three modes of heat transfer. First is conduction, convection, and radiation. But before that, let's define first heat transfer. Heat transfer is the movement of thermal energy from a region of higher temperature to a region of lower temperature. These movements continue until thermal equilibrium is reached, meaning that temperatures become equal. The driving force behind heat transfer is a temperature difference. First mode of heat transfer is conduction. Conduction is the transfer of heat through direct contact between molecules. It occurs primarily in solids, where molecules are closely packed together. When one molecule vibrates due to heat, it transfers energy to its neighboring molecules. A chain reaction that spreads the heat. Materials with high thermal conductivity like metals transfer heat quickly through conduction, while materials with low thermal conductivity like wood or air transfer heat slowly. Next mode of heat transfer is convection. Convection is the transfer of heat through the movement of fluids, like liquids or gases. When a fluid is heated, its density decreases, causing it to rise. Cooler, denser fluid sinks to replace it, creating a cycle of movement that distributes heat. This process is known as a convection current. Convection is a major mechanism for heat transfer in the atmosphere and oceans. The last mode of heat transfer is radiation. Radiation is the transfer of heat through electromagnetic waves. These waves can travel through empty space, unlike conduction and convection, which require a medium. The sun's energy reaches the earth through radiation. All objects emit radiation, but the amount and type of radiation depend on the object's temperature. Hotter objects emit more radiation at a shorter wavelengths. Example for that is visible light and ultraviolet radiation, while cooler objects emit less radiation and at longer wavelengths, which is the infrared radiation. So now let's have an experiment. This experiment shows the three methods of heat transfer, which is the conduction, convection, and radiation, using a pot of water being heated on a stove. Let's break down each process step by step. First mode of heat transfer applied is radiation. First is the electric stove tops heating elements emits infrared radiation. This is electromagnetic radiation, invisible to the human eye, that carries thermal energy. This radiation travels directly to the bottom of the pot. The wavy lines in the diagram represents the infrared radiation. The pot absorbs this radiation, which is the darker colored surfaces, absorb radiation more efficiently than lighter ones. Next is conduction. Once the bottom of the pot absorbs the radiation, its temperature increases. The heat energy is transferred through the metal of the pot itself. This is conduction, the transfer of heat through direct contact between molecules. The heat conducts from the bottom of the pot through the sides and eventually to the water at the bottom. And then lastly, the convection. As the water at the bottom of the pot is heated by conduction, its temperature rises and its density decreases. This less dense, warmer water rises. Then cooler, denser water from the top of the pot sinks to replace it. This creates a circular current, or what's called the convection current, that distributes heat throughout the water. The arrows in the video illustrate this movement. The arrow shows in the diagram illustrate this movement. To sum it up, the stove top heats the pot through radiation, and then the pot heats the water through conduction, and then the heated water circulates and distributes heat through convection. All three methods work together to heat the water in the pot. The same principle applies to many natural processes, including the heating of the Earth's atmosphere and oceans.
Have you ever noticed how warm your face feels on a bright cold day? Even when the air around you is chilly. That's because the sun isn't just warming the air, it's transferring energy directly to your skin through radiation. Radiation travels in the form of waves, like ripples on a pond. But these waves are special. They carry energy and have both magnetic and electrical properties, which is why we call them electromagnetic waves. These waves don't need air or any other medium to travel. They can even zip through the vacuum of space. Now, these electromagnetic waves come in different sizes or wavelengths. Think of it like this. The longer the wave, the less energy it carries. The shorter the wave, the more powerful it is. The sun, being a super hot ball of gas with a surface temperature of about 6,000 Kelvin, emits mostly shortwave radiation, including the visible light we see. Earth, on the other hand, is much cooler, with an average surface temperature of about 288 Kelvin, so it emits longer wavelengths. mainly in the infrared region, which we can't see. Now, every object, even you and me, is constantly emitting and absorbing radiation. A perfect absorber and emitter is called a black body. It doesn't have to be black, it just have to absorb and emit all possible radiation. The Sun and Earth are pretty close to being black bodies, which help us understand how they interact. So, the Sun's energy reaches Earth, warms the surface, and then the surface warms the air above it through conduction and convection. This is like a pot of water on a stove. The heat from the stove warms the bottom of the pot, and then the hot water rises, creating currents. But here's the key to understanding Earth's climate. It's all about balance. Earth must emit as much energy as it receives to maintain a stable temperature. Let's break down this energy balance. The process begins with 100 units of solar radiation entering the Earth's atmosphere. This represents the solar constant, which is the average amount of solar energy received per unit area at the top of the atmosphere. About 30 units are reflected back into space by clouds, ice, and other surfaces. This is like a mirror reflecting sunlight. We call this reflectivity albedo. Clouds, for example, have a high albedo, reflecting a lot of sunlight. Snow and ice are even more reflective. Water, on the other hand, reflects less sunlight. The remaining 70 units are absorbed by the atmosphere and Earth's surface. This absorbed energy warms our planet. Now, Earth's surface is constantly emitting infrared radiation, like a warm body radiating heat. About 117 units of infrared radiation are emitted upwards. But here's where the greenhouse effect comes in. The atmosphere containing gases like water vapor and carbon dioxide absorbs a large portion of this infrared radiation. This is like a blanket trapping heat. These gases are called greenhouse gases because they act like the glass roof of a greenhouse, allowing sunlight in but trapping heat inside. Now, let's look at what happens to the infrared radiation emitted by Earth. Some of it escapes directly into space through a special window in the atmosphere where greenhouse gases don't readily absorb radiation. But most of it is absorbed by greenhouse gases like water vapor and carbon dioxide. These greenhouse gases then re-emit this infrared radiation in all directions, including back down to Earth's surface. This process is a major contributor to the warming of our planet. This constant exchange of energy between the sun, Earth's surface, and the atmosphere creates a delicate balance that keeps our planet at a habitable temperature. But this balance is being disrupted by human activities. We are adding more and more carbon dioxide to the atmosphere by burning fossil fuels and cutting down trees. This extra carbon dioxide acts like an extra blanket, trapping more heat and causing our planet to warm up. This warming trend called climate change is causing a whole range of problems, including rising sea levels, more extreme weather events, and changes in ecosystems. Understanding these processes is crucial for tackling the challenges of climate change. Now that we have explored Earth's energy balance, let's shift our focus to the world of solar particles, the aurora, and space weather.
For our last topic, we will be talking about solar particles, the aurora, and the space weather. Solar wind and solar particles. The sun constantly ejects high-energy particles, primarily electrons and protons, into space. These solar winds varies in intensity depending on the solar activity, such as sunspot, solar flare, and coronal mass ejections, or CMES. When these energetic particles reach Earth, they interact with our planet's magnetosphere, a protective magnetic field that shields us from harmful radiation. Next is the formation of the aurora, or what's called the aurora borealis. One of the most visible effects of solar particles interacting with Earth's atmosphere is the aurora borealis, or the northern lights, and aurora australis, or the southern lights. Here's how they form. First is, solar wind particles collide with Earth's magnetosphere, traveling along magnetic field lines toward the poles. And then second is particles enter the upper atmosphere and collide with gases like oxygen and nitrogen. And then third is, these collisions excite the gas molecules, causing them to emit light. Oxygen produces green and red auroras, while nitrogen emits blue and purple hue. These auroras appear as dancing lights in the night sky, mostly commonly seen near in the Arctic and Antarctic regions. Space weather can have significant effects on technology and daily life. Major solar storms such as coronal mass ejections, or CMES, that can disrupt GPS and communication systems. High-energy solar particles can interfere with satellites, causing navigation and communication errors. Lastly is pose risk for astronauts and airlines. Increased radiation exposure can be dangerous for astronauts in space and even for airline passengers on high-altitude polar flights.
Wow, what an incredible journey that was! We've seen how the sun's energy powers our world, from keeping us warm to creating the natural aurora.
All connected by the amazing power of energy. Remember, keep exploring and wonders all around you.
Thank you for joining us on Energy Explorer Show.
Until next time,